In mathematics, function composition is the pointwise application of one function to the result of another to produce a third function. For instance, the functions f, x, y and g, y, z can be composed to yield a function which maps x in x to g in z. Intuitively, if z is a function of y, and y is a function of x, then z is a function of x. The resulting composite function is denoted gf, xz, defined by E equals g, for all x in x. The notation gf is read as g circle f, or g round f, or g composed with f, g after f, g following f, or g of f, or g on f. Intuitively, composing two functions is a chaining process in which the output of the first function becomes the input of the second function. The composition of functions has some additional properties. Examples: composition of functions on a finite set. If f equals, and g equals, then gf equals. Composition of functions on an infinite set. If f is given by f equals 2x plus 4 and g is given by g equals x3, then equals f equals 2 by 3 plus 4, and equals g equals 3. If an airplane's elevation at time t is given by the function h, and the oxygen concentration at elevation x is given by the function c, then describes the oxygen concentration around the plane at time t. Properties. The composition of functions is always associative, a property inherited from the composition of relations. That is, if f, g, and h are three functions with suitably chosen domains and codomains, then f equals h, where the parentheses serve to indicate that composition is to be performed first for the parenthesized functions. Since there is no distinction between the choices of placement of parentheses, they may be left off without causing any ambiguity. In a strict sense, the composition gf can be built only if f's codomain equals g's domain. In a wider sense, it is sufficient that the former is a subset of the latter. Moreover, it is often convenient to tacitly restrict f's domain such that f produces only values in g's domain. For example, the composition gf of the functions f equals 9 minus x2 and g 0 plus infinity, defined by g equals square root x, can be defined on the interval minus 3 plus 3. The functions g and f are said to commute with each other if gf equals fg. Commutativity is a special property, attained only by particular functions, and often in special circumstances. For example, x plus 3 equals x plus 3, only when x0. The picture shows another example. The composition of one-to-one functions is always one-to-one. Similarly, the composition of two onto functions is always onto. It follows that composition of two bijections is also a bijection. The inverse function of a composition has the property that -1 equals. Derivatives of compositions involving differentiable functions can be found using the chain rule. Higher derivatives of such functions are given by Faa-Bruno's formula. Composition monoids. Suppose one has two functions f, xx, xx having the same domain and codomain. These are often called transformations. Then one can form chains of transformations composed together, such as ffgf. Such chains have the algebraic structure of a monoid, called a transformation monoid or composition monoid. In general, transformation monoids can have remarkably complicated structure. One particular notable example is the Rham curve. The set of all functions f, xx is called the full transformation semigroup or symmetric semigroup on X. If the transformation are bijective, then the set of all possible combinations of these functions forms a transformation group, and one says that the group is generated by these functions. A fundamental result in group theory, Cayley's theorem, essentially says that any group is in fact just a group of permutations. The set of all bijective functions f, xx forms a group with respect to the composition operator. This is the symmetric group, also sometimes called the composition group. In the symmetric semigroup, one also finds a weaker, non-unique notion of inverse because the symmetric semigroup is a regular semigroup. Functional powers. If y(x), then f(xy) may compose with itself. This is sometimes denoted as f2, that is, equals f equals f2 equals f equals f3, or generally, for any natural number n2. The nth functional power can be defined inductively by fn equals ffn minus 1 equals fn minus 1f. Repeated composition of such a function with itself is called iterated function. By convention, f0 is defined as the identity map on F's domain, IDX. If even y equals x and f(x) admits an inverse function f-1, negative functional powers f-n are defined for n greater than 0 as the opposite power of the inverse function, f-n equals n. Note: if f takes its values in a ring, there is a risk of confusion, as fn could also stand for the n-fold product of f, e.g., f2 equals ff. For trigonometric functions, usually the latter is meant, at least for positive exponents. For example, in trigonometry, this superscript notation represents standard exponentiation when used with trigonometric functions. Sin2 equals sin. However, for negative exponents, it nevertheless usually refers to the inverse function, e.g., tan-1 equals arctan1, tan. In some cases, when, for a given function f, the equation g equals f has a unique solution g, that function can be defined as the functional square root of f, then written as g equals f1/2. More generally, when gn equals f has a unique solution for some natural number n greater than 0, then fm(n) can be defined as gm. Under additional restrictions, this idea can be generalized so that the iteration count becomes a continuous parameter. In this case, such a system is called a flow, specified through solutions of Schrodinger's equation. Iterated functions and flows occur naturally in the study of fractals and dynamical systems. Alternative notations. Many mathematicians, particularly in group theory, omit the composition symbol, writing GF for GF. In the mid-20th century, some mathematicians decided that writing GF to mean first apply F, then apply G was too confusing and decided to change notations. They write XF for F and G for G. This can be more natural and seems simpler than writing functions on the left in some areas. In linear algebra, for instance, when X is a row vector and F and G denote matrices and the composition is by matrix multiplication, this alternative notation is called postfix notation. The order is important because matrix multiplication is non-commutative. Successive transformations applying and composing to the right agrees with the left to right reading sequence. Mathematicians who use postfix notation may write FG, meaning first apply F and then apply G. In keeping with the order the symbols occur in postfix notation, thus making the notation FG ambiguous. Computer scientists may write FG for this, thereby disambiguating the order of composition. To distinguish the left composition operator from a text semicolon, in the Z notation the character is used for left relation composition. Since all functions are binary relations, it is correct to use the fat semicolon for function composition as well. Composition operator. Given a function g, the composition operator CG is defined as that operator which maps functions to functions, as composition operators are studied in the field of operator theory. In programming languages, function composition appears in one form or another in numerous programming languages. Multivariate functions. Partial composition is possible for multivariate functions. The function resulting when some argument g of the function f is replaced by the function g is called a composition of f and g in some computer engineering contexts, and is denoted f g equals g when g is a simple constant b. Composition degenerates into evaluation. whose result is also known as restriction or cofactor. In general, the composition of multivariate functions may involve several other functions as arguments, as in the definition of primitive recursive function. Given f, a nary function, and nmary functions g1, gn, the composition of f with g1, gn, is the mary function. This is sometimes called the generalized composite of f with g1, gn. The partial composition in only one argument mentioned previously can be instantiated from this more general scheme by setting all argument functions, except one, to be suitably chosen projection functions. Note also that g1, gn can be seen as a single vector, tuple-valued function in this generalized scheme, in which case this is precisely the standard definition of function composition. A set of finitary operations on some base set X is called a clone if it contains all projections and is closed under generalized composition. Note that a clone generally contains operations of various arities. The notion of commutation also finds an interesting generalization in the multivariate case. A function f of arity n is said to commute with her function g of arity m if f is a homomorphism preserving g, and vice versa, i.e., a unary operation always commutes with itself, but this is not necessarily the case for a binary operation. A binary operation that commutes with itself is called medial or entropic. Generalizations composition can be generalized to arbitrary binary relations. If Rx times Y and Sy times Z are two binary relations, then their composition Sr is the relation defined as X times Z, YY, Rs. Considering a function as a special case of a binary relation, function composition satisfies the definition for relation composition. The composition is defined in the same way for partial functions, and Cayley's theorem has its analog called Wagner-Preston theorem. The category of sets with functions as morphisms is the prototypical category. The axioms of a category are in fact inspired from the properties of function composition. The structures given by composition are axiomatized and generalized in category theory, with the concept of morphism as the category theoretical replacement of functions. The order inversion in the formula -1 equals applies for groups in general and for the inverse relation. Each of these is a dagger category. Typography. The composition symbol is encoded as U plus 2218 ring operator. See the degree symbol article for similar appearing Unicode characters. In text, it is written circ.